Okay, let's continue. Modular arithmetic. So we see equality of integers AB is a strict condition. Can we weaken equality to a congruence such that some essential properties of equality still hold? Like, so equality is a strict condition. Equality of two integers is a strict condition. Can we weaken equality operator to a congruence operator such that some essential properties of equality still hold? Like, we want if integers a is congruent to b and b is congruent to c, then we want a to be congruent to c if integers, we want to be able to add congruences like we add equalities. If integers a is congruent to b and c is congruent to d, then a plus c is congruent to b plus d. If integers a is congruent to b and c is congruent to d, then AC is congruent to PD. Can we weaken the equality operation to a congruence operation such that some essential properties of equality still hold? Like, if A is congruent to B and B is congruent to C, we can say A is congruent to C. So we can have chains of, so I'll write it here. So we can have chains of congruences. So we can add congruences like we add equalities. So we can multiply congruences. Well, let's show that. So that we can add congruences and so that we can multiply congruences. Can we weaken equality to a congruence such that these properties hold? We can have chains of congruences, we can add congruences, and we can multiply congruences. Can we weaken equality to such an operation? This is a question. So yes, we can. So definition: congruence modulo d. Let d be a natural number. Let a, b be integers. We say a is congruent to b modulo d if a equals b plus dk for some integer k. So we say a is congruent to b modulo d if a is b plus dk for some integer k. That is, A congruent to B modulo D means A is B is equal to B up to a multiple of D. We say A is congruent to B if A is equal to B plus some multiple of D. Okay, so this is congruence operation. Congruence modulo D. So we can ask, let D be a natural number. Does congruence modulo D satisfy the above essential properties? So the essential properties I will state again. Essential properties like if integers, we want to be able to take chains of congruences. If integers A is congruent to B mod D and C is congruent to E mod D, then A is congruent to E mod D. We want this property. If integers A is congruent to B mod D and C is congruent to E mod D, then A plus C is congruent to B plus E mod D. So we want to be able to add congruences so that we can take chains of congruences. This is so that we can add congruences. So we also want to be able to multiply congruences. If A is congruent to B mod D and C is congruent to, so the above essential properties of equality, like, or else the above essential properties like, so does congruence satisfy these essential properties? See, if C is congruent to E mod D, then AC is congruent to BE mod D. This is so that multiplication is so that we can multiply congruences like we multiply equality. So we should be able to take chains of congruences like we take chains of equalities. We should be able to add congruences like we can add equalities. We should be able to multiply congruences like we multiply equalities. Do we have these essential properties for congruence modulo D? This is the question. Does congruence modulo D satisfy the above essential properties? So it turns out yes. So we'll prove it step by step. So observation, or I'll write transitivity of congruences. The ability to take chains of congruences is called transitivity. transitivity of congruences. Let t be a natural number. Let A be congruent to B mod D and B is congruent to, sorry, I meant something else. B is congruent to C. Then A is congruent to C. Did I write it correctly here? Yeah, if A is congruent to B and B is congruent to C, we want A is congruent to C. B is congruent to C mod D. Let A be congruent to B mod D and B be congruent to C mod D. Then we have A is congruent to C mod D. So we can take chains of congruences. So proof is from the definition. So A is congruent to B mod D. So A is B plus dk1 and B is C plus dk2 for some integers k1 and k2 by definition of congruences. Hence A is equal to C plus dk2 plus dk1. So I'll write it again. A is B plus dk1 equals C plus dk2 plus dk1. So this is C plus d into k1 plus k2. Hence A is congruent to C mod D as needed. So we can take transitivity of congruences. We'll prove the second property. Observation. Addition of congruences. Let D be a natural number. Let A, B be integers, or I'll directly let integer A be congruent to B mod D and C is congruent to E mod D. Then we can add these congruences to get A plus C is congruent to B plus E mod D. So proof is, as always, we write A is B plus, since A is congruent to B mod D, A is B plus dk1 and C is E plus dk2 for some integers k1 and k2. Hence A plus C is equal to B plus E plus D times k1 plus k2. Hence A plus C is congruent to B plus E mod D. Okay, so we can add congruences. We can have we have transitivity of congruences. So we have transitivity of congruences. We can add congruences. We need to check if we can multiply congruences. Observation. Multiplication of congruences. Let D be a natural number. Let A be congruent to B mod D and C is congruent to E mod D. Then we have AC is congruent to BE mod D. So the proof is as usual. A is B plus dk1 and C is E plus, we know this, C is E plus, A is B plus dk1 and C is E plus dk2 for some integers k1 and k2. Hence AC is B plus dk1 times E plus dk2, which is BE plus D times bk2 plus, okay, since we are in the beginning stages, let me write, okay, I'll not write the distributivity again, or fine, I'll write, to emphasize the distributivity law, I'll write it again. dk1 times E plus B plus dk1 times dk2 equals BE plus dk1E plus bdk2 plus d square k1 k2. So this is BE plus d times k1E plus bk2 plus d k1 k2. Hence AC, the product AC is congruent to BE mod D as needed. Right, so we do have the multiplication property as well. So this congruence modulo D satisfies some of the essential properties of equality, like transitivity, addition, and multiplication. Okay, so why do we care about such a modification of equality? Well, here's an example. Here are some examples to show the usefulness of these. So this example is for divisibility by 9. Or I'll write here, so let an times a naught, a1, a naught be an n-digit integer. How can we write divisibility by 9? Let this be an n-digit integer. How can we decide if the n-digit integer is divisible by 9, that is congruent to 0 mod 9? How can we decide if the integer is 0 plus a multiple of 9? So let's do that. So firstly, an, this n-digit integer, is a0 plus 10 power 1 times a1 plus so on till 10 power n times an. For example, 76293 is 3 plus 10 power 1 times 9 plus 10 square times 2 plus 10 cube times 6 plus 10 power 4 times 7. So this is this is an example. So this is the number, and so the n-digit number can be expressed as in terms of the powers of 10 by definition. Now powers of 10 and the digits. Now so a1 a0. So okay, let me write multiplying 10 is congruent to 1 mod 9. So 10 is 1 plus 9, right? So 1 plus a multiple of 9. Hence 10 is congruent to 1 mod 9. Multiplying 10 is congruent to 1 mod 9 with itself. We have 10 power n is congruent to 1 power n mod 9, etc. Hence, so the n-digit number, which is a0 plus 10 power 1 times a1 plus so on till 10 power n times an, this is congruent to a0 plus 1 power 1 times a1 plus 1 power n times an mod 9. Hence an a1 a0, this n-digit number is congruent to 0 mod 9 if and only if the sum of digits a0 plus a1 plus so on till an is congruent to 0 mod 9. So we'll look at an example. Is 932100741 divisible by 9? So we have 932100741 is congruent to 9 plus 3 plus 2 plus 1 plus 0 plus 7 plus 4 plus 1 mod 9. So we'll take, so this is congruent to 0 plus 3 plus 2 is 5 plus 3 plus 2 is 5, and 9 is congruent to 0 mod 9. 3 plus 2 is congruent to 5 mod 9 plus or let's take 3 plus 2 plus 1 6 mod 9 plus 0 plus 7 plus 4 is 11, which is congruent to 2 mod 9 plus 1 mod 9. So this is congruent to 0 mod 9. So we took a chain of congruences and we saw that 932100741 is congruent to 0 mod 9. Hence 932100741 is divisible by 9. Okay, let me, so in the starting I wrote that is a is congruent to b means a is equal to b up to a multiple of d. To be more clear, a is equal to b plus a multiple of d. So every time you see a is congruent to b mod d, think of this relation, that a is b plus a multiple of d. Okay, so here 932100741 is, we can take these congruences. We saw that the n-digit number is congruent to its sum of digits mod 9. So 932100741 is congruent to the sum of digits mod 9, modulo 9, and this sum of digits is again congruent to 0 plus 6 plus 0 plus 2 plus 1 mod 9. So, and this is again further congruent to 0 mod 9. Hence, the original number is congruent to 0 mod 9, and the original number is divisible by 9. So this is an example of the usefulness of the congruence notation, having such congruences, some weaker notion of equalities. So an even better example would be the divisibility by 11 thing. Divisibility by 11. So as above, let an times a1 tilde a1 a0 be an n-digit integer. How can we decide if this n-digit integer is divisible by 11? That is 0 plus a multiple of 11 is congruent to 0 mod 11. How can we decide if this integer is 0 is congruent to 0 mod 11? So let's see. An, so the n-digit integer is a0 plus 10 power 1 times a1 plus so on till 10 power n times an, multiplying 10 is congruent to minus 1 mod 11. So 10 is minus 1 plus 11. So it is 10 is minus 1 plus a multiple of 11. Multiplying 10 is congruent to minus 1 mod 11 with itself. We have 10 power n is congruent to minus 1 power n mod 11, etc. Hence, the n-digit number is a0 plus 10 power 1 times a1 plus 10 power n times an. So this, when we take congruence modulo 11, this becomes minus 1 times a1 plus minus 1 power n times an. This is mod 11. Hence, the original number is congruent to 0 mod 11, that is divisible by 11 if and only if the alternating sum of digits, or I'll just write alternating sum of digits a0 minus a1 plus a2 plus so on till minus 1 to the n an is congruent to 0 mod 11. Example. Or I don't need to write the alternating sum of digits. Or okay, let's leave it here. Example. Is this long integer 138363434 divisible by 11? So answer. We saw that 138363434 is congruent to 4 minus 4. So you take a0 minus a1 plus a2 plus so on till minus 1 power n. So a0 is 4, a1 is 4, so minus a1 plus a2 is 4 plus 4, minus a3 is minus 3, so on, plus 4 minus 3 plus 6 minus 3 plus 8 minus 3 plus 1. So this is this mod 11. 4 plus 4 minus 4 plus 4 minus 3 plus 4 minus 3 plus 6 minus 3 plus 8 minus 3 plus 1. So this long number is just congruent to this simple number mod 11. So 4 minus 4, we can just pair these off. So 0 plus 1 plus 1 plus 3 plus 5 plus 1 mod 11. So each term is congruent to, so 4 minus 4 term is congruent to 0 mod 11, 4 minus 3 is congruent to 1 mod 11, so on. We can add those congruences and we would get this whole alternating sum is congruent to 0 plus 1 plus 1 plus 3 plus 5 plus 1 mod 11. This again is congruent to 5, 6, 7, 8, 9, 10, 11. So this is congruent to 0 mod 11. So we took a chain of congruences and saw that this big integer is congruent to 0 mod 11. Hence, the big integer 138 3634 3444 is divisible by 11. Okay. That's all for this part. See you in the next part.